Start with the failure. Load a 70 billion parameter neural network in its native 16-bit format onto a standard consumer computer, and the system instantly crashes. This out-of-memory kernel panic doesn't happen because the processor lacks the computational power to do the math. It happens because the system cannot move the data fast enough. This spatial divide between the storage drive, the system RAM, and the processor cache creates what engineers call the memory wall. The physical bandwidth limit of your hardware throttles execution. Massive models built for training use uncompressed 16-bit floating-point decimals. Moving 140 gigabytes of those precise decimals across a standard consumer PCIe bus is structurally incompatible with local hardware. Making local execution possible means we have to stop treating artificial intelligence as a pure algorithmic problem and start treating it as a raw data serialization problem. The true barrier to running massive models on local devices is the physical reality of memory architecture. The open-source community surrounding the llama.cpp engine engineered a precise structural answer, the GPT-Generated Unified Format, or GGUF. GGUF is a strictly self-contained binary file container. It removes complex, resource-heavy Python abstractions, operating as a zero-dependency package. Its architecture is designed to let the operating system stream precisely aligned slices of neural network weights directly to the processor, avoiding the need to load a massive file entirely into active VRAM. The catch is that streaming models this way requires extreme compression. The data must be squeezed from 16-bit down to 4-bit integers. In traditional deep learning, compressing parameters this aggressively destroys the network's reasoning capabilities. Pacing speeds up slightly. To compress extreme intelligence into a 4-bit space without breaking it, GGUF relies entirely on a mathematical framework formalized over 200 years ago, the statistical geometry of Carl Friedrich Gauss. GGUF functions as a structural bridge between physical hardware limits and 200-year-old statistical mathematics. GGUF operates sequentially. First, a 32-bit magic header, then an extensible key-value metadata store replacing older, brittle formats. Next, the tensor info array uses 64-bit offset pointers to locate raw data inside the massive tensor data blob, which snaps perfectly to a 32-byte grid. That geometric alignment is deliberate. It triggers the operating system's mmap, memory-mapped file system call. Instead of reading a 40-gigabyte file entirely into physical RAM, mmap translates the file's exact coordinates on the storage drive directly to virtual memory addresses. This means the processor can stream only the required 32-byte slices into its highest speed cache exactly when a calculation needs them, gracefully distributing the massive workload across both system RAM and GPU VRAM. The file's binary layout is engineered to mathematically mirror the physical memory bus, turning passive disk storage directly into an active execution layer. But traversing that memory bus rapidly still demands smaller data. The weights have to be shrunk through quantization to prevent traffic jams on the motherboard. The mathematical goal of quantization is simple. Take highly precise 16-bit floating-point decimals, calculate a global scaling factor, and round them down into much smaller integer approximations. This scatter chart shows a layer's weight distribution. A single extreme outlier stretches the compression scale wildly. The 4-bit interval lines are pushed so far apart that the normal weights are lumped into a single inaccurate bucket, losing all nuance. To minimize the error between the original massive values and the compressed outputs, engineers use the method of least squares, developed by Carl Friedrich Gauss in the 18th century. Gauss's theorem works perfectly, but it comes with a strict mathematical caveat. For this method to provide an optimal, unbiased estimate, the underlying data errors must follow a normal, symmetrical Gaussian distribution, a classic bell curve. And that is the crisis of local AI. The heavy-tailed weights of a large language model violate Gauss's normal distribution assumption. Unless those weight distributions can be mathematically corralled into a bell curve, extreme compression will inevitably strip the model of its ability to reason. GGUF solved this quantization crisis at the architectural level with a technique called K-quants, block-based quantization. Instead of calculating one uniform scale for an entire massive layer, K-quants aggressively fracture the weight matrices into isolated microblocks of exactly 32 weights. Focusing on just 32 numbers isolates the disruptive variance. Stripped of global outliers, these 32 data points naturally align into a tight, near-perfect Gaussian bell curve. GGUF then calculates a distinct independent scaling factor exclusively for this specific shape, ensuring zero wasted mathematical space. During execution, the inference engine pulls these optimized blocks from disk, dynamically dequantizes them back into floating point numbers inside the processor's high-speed cache, and completes the matrix multiplication. This yields extraordinary operational efficiency, retaining 95% of original intelligence while stripping 70% of size. By enforcing strict 19th-century Gaussian geometry at the microblock level, K-quants allow the hardware to circumvent the memory wall while preserving the neural network's intelligence. Because GGUF solves the memory wall via statistical compression, a computer's actual token generation speed scales cleanly alongside its available memory bandwidth. This benchmark matrix highlights the hardware realities. Older cards with 6 GB of VRAM are strangled by slow PCIe swapping, but modern 24 GB cards achieve near-instant latency because the highly quantized model fits entirely within VRAM. This dynamic scaling establishes GGUF as the standard for edge devices and hardware utilizing unified memory architectures, like Apple's M-series chips. Major enterprise developers, including IBM with their Granite series, have explicitly integrated GGUF pipelines to guarantee their models interoperate smoothly with the open-source ecosystem. However, this dominance on local machines reveals GGUF's sharpest structural limitation. It struggles in high-throughput, multi-tenant enterprise data centers. The underlying engine relies on standard sequential C-level queuing. It cannot efficiently manage thousands of uncoordinated simultaneous API requests the way cloud-native frameworks using page detention continuous batching can. Therefore, GGUF intentionally sacrifices centralized multi-user scalability. It trades data center throughput for absolute localized determinism on a single stream. But operating as a fully self-contained, self-describing file introduces a severe architectural vulnerability. Because the parser automatically reads the key value store to configure the model, attackers can inject untyped, malicious strings into the metadata. In early 2026, this exact mechanism was used to force parsing engines into attempting impossible memory allocations, triggering total system denial of service. And a more insidious threat exists: inference-time template poisoning. By injecting arbitrary Jinja2 instructions directly into the file's metadata, a malicious actor can covertly rewrite the entire chat template. This silently hijacks how the model interprets user prompts, effectively turning the network against the operator. Because standard enterprise security scanners look for Python executables or pickle files, these text-based behavioral backdoors completely bypass traditional detection. Despite these risks, the format is a refined example of low-level systems engineering, aggressively pruning abstraction to interface directly with the physics of memory architecture. Executing frontier models locally depends on this dual legacy, mastering physical silicon pathways while relying on 200-year-old statistical geometry to preserve the intelligence within.